Welcome to Mathematics 041, Pre-Algebra. Let's get started with the first section. We're looking at the set of real numbers. A set is a collection of objects whose contents can be clearly determined. If the set is finite, we can describe the set completely by simply listing all the objects in the set and enclosing the list in curly braces. The objects in a set are called the elements in a set. So again, finite means there's a definite specific number. The opposite of finite would be infinite. The numbers are broken down into different categories, so to speak. First, we have our natural numbers. Those are counting numbers, 1, 2, 3, and so on. Notice the 3 dots at the end. That means that you can keep counting on forever. And there's those curly braces that it mentions before. When we add the number 0 to it, we get the whole numbers. And then with the integers, we're adding the negatives onto it as well. And notice with the negatives, we're still dealing with like counting numbers, -5, -4, -3. We don't get into parts of a whole, such as your fractions or your decimals, until we get into your rational numbers. Rational numbers are any number that can be written as a fraction. And whole numbers can be written as a fraction because we can write anything over 1. Remember what you're using as a denominator, that bottom number is thinking of as like dividing, and so 5 over 1, 5 divided by 1 is still 5. And this includes terminating and repeating decimals. Terminating means ending, so 0.5 can be written as 1/2, or repeating decimals such as 1/3. If you try and divide that, you'll get 0.3333 forever, and so 0.3 repeating is 1/3 as a fraction. And then we have numbers that cannot be written as a fraction, and those are called the irrational numbers. They include most roots, so your square roots that aren't perfect, which means there's no number times itself that gives you an answer. And an example of a root that could be written as a fraction is the square root of 9. The square root of 9 is 3 because 3 times 3 is 9. But for example, the square root of 5 would be irrational because there's no whole number times itself that would give you 5 as an answer. And then numbers like pi. We know that we can round pi to use 3.14 when we're dealing with calculations with circles, but the actual value of pi never repeats and ends, and so it is considered an irrational number. So if we look at it visually, the set of real numbers is formed by combining the rational numbers and the irrational numbers. I know your textbook has it in a box instead of a circle, but I just found this one that was nice and pretty on the internet to show for the slides. As you can see, oops, sorry, I'm trying to use my touchpad for this. As you can see, all rational numbers have integers, whole numbers, and natural numbers. All integers have whole numbers and natural numbers. All whole numbers have naturals. So that's how they're showing you the kind of the nested different sections. And notice irrational numbers are completely by themselves over here because no irrational number can be irrational at the same time. So for our first example, we're going to look at a set of numbers, and we're going to look at putting them on a number line. And so as you can see, we have 0 in the middle of our negatives and positives. So our negative numbers go to the left, and notice we have -1 closer to 0 than 2, 3, 4, and so on. So we're counting what feels like backwards to go to the negatives. And then to the right of the zeros are positives. So if we're going to locate some of the numbers on the number line, -7, we can see right here. -3/4. And if you think of 3/4, I always think of quarters. 3/4 is 75 cents. So we have -0.75, which is a little bit smaller than -1, so let's put it right about here. And I apologize for my handwriting. I'm trying to use a mouse to write with, which does not work well. Then we can see we have 0 here. And then we have the square root of 5. And so that's a number that you're going to have to use your calculator to be able to put on a number line, because the square root of 5 doesn't come out evenly, like I mentioned before. There's no number times itself that gives you 5 as an answer. And so to find it in the calculator, you're going to want to locate your square button, which usually looks like an x to the second power. And above that, you should see a root symbol. And so you'll need to use your shift and the x squared button. Squared means 2. And again, above it, you should see a little symbol like that. And so if you hit second and then that button, you should get that symbol that is your square root symbol. And then if you type 5 and equal sign, you should get 2.23606, and it continues on. So again, it's irrational because it's not going to repeat and it's not going to end, but it's close to 2.25. So just about a quarter more than 2. So we're going to put it right about here. And we already mentioned that pi is approximately 3.14, so it's just after the 3. I'm going to put it down here. And then 7.3, so a little bit after the 7. And then the square root of 81. Again, the square root means what number times itself gives you 81 as an answer. 9 times 9 is 81. So the square root of 81 is the same as 9, just written a different way. And if you weren't sure about that, you could use your calculator to help you find that. And so our square root of 81 is right here with our 9. So looking at the set of numbers, let's identify first the natural numbers. Remember, the natural numbers are the counting numbers, 1, 2, 3, and so on. We don't see that in our set until we remember that the square root of 81 is 9. And 9 is a counting number, and so we will use the square root of 81 as our natural number in the set. The whole numbers, remember, adds 0 to the list of natural numbers. And so we do have a 0 in our set. So 0 and the square root of 81 are our two whole numbers. When we have our integers adding to that, we're adding the negative numbers that are like negative counting numbers. And so that adds -7 to our list. And remember, the list of integers includes a list of whole numbers and a list of natural numbers. And so we have our 0 and our square root of 81 already for integers, but we're going to put our -7 up front just to keep them in order. And technically, we can be putting all of these in those curly braces because each subgroup is called a subset, and it is a set itself. So here's the set of all natural numbers that are in our list with just the square root of 81, and so on. And so when we add our rational numbers to it, remember we're adding to our natural, our whole, and our integers any number that can be written as a fraction, which includes our repeating decimals, and our fractions and whole numbers. But I noticed when I was mentioning rational numbers Then I forgot one of the numbers up here. 0.6, notice that bar above that, that means it repeats, so 0.6 with a line means 0.6666, and it could keep going on forever. And that fraction is actually 2/3. If you divide 2 divided by 3, you'll get 0.6 repeating. And so 2/3 is about here, let's say, on our number line. Let me write it the way we have it in our list. 0.6 repeat. There we go. And so we can add that to our list. And one thing that might be easier to do is to identify the irrational numbers, because remember, a number is either rational or irrational. And so if it's irrational, then it's not going to be included in the rational list, and your irrational list is going to be a lot smaller. So remember, irrational are numbers that are square roots that don't come out perfectly, and we saw that with the square root of 5. And then any number such as pi that we assign the Greek letter to represent this crazy value that we get. And so those are our two that are irrational. So all the other numbers are going to be rational. So if we look at our list, we had -7 to start. Again, I apologize for my messy writing, trying to write with a mouse. And then we had -3/4. And then we had 0. And our 0.6 repeating. And we had the square root of 5, which we already used as irrational, and pi, which we used as irrational. And so we have 7.3 and our 9, which is written as the square root of 81. And again, let's throw those braces around it to show that it is the set of rational numbers from our list. And we'll add the set symbol to our irrational numbers. And then all together, rational plus irrational equals a real number. So instead of making you painfully wait for me to write all the list down again, I'm just going to put the word all there to show you. But technically, you would write all the numbers, -7, -3/4, 0, 0.6 repeating, square root of 5, pi, 7.3, and the square root of 81. So now I want us to think about these groups and come up with numbers that fit certain criteria or descriptions. So a rational number that is not an integer. So rational number can be written as a fraction, rational ratio fraction. That helps me remember that. That is not an integer. Our integer was -0, and positive natural numbers, counting numbers. So -3, -2, -1, 0, 1, 2, 3. So as long as we give a fraction that doesn't equal a whole number, we are good. So let's do 7/8 as an example. And irrational, remember, those are the ones that do not terminate, do not repeat. And the easiest way to do that is do the square root of a number that is not some number times itself. So the square root of 2. There's no number times itself that gives 2 as an answer. And you can check it by doing the square root of the number if you're not sure, just to make sure it gets you this big long thing instead of a nice even number like the square root of 16 would be 4. So we couldn't use that. And now we have an integer that is not a whole number. Remember, whole numbers is 0 and our natural numbers, or 0 and our counting numbers. And so that means we need to take a negative number to get an integer that is not a whole number. So let's do -10 for that one. Obviously, there are many more examples that we could choose, but that's just one example of each. Here it asks us to express each rational number as a decimal. And so we want to see what decimal is equivalent to 3/5. Well, as a fraction, remember the bottom tells you how many make up a whole. And so I was taught down and out because the only way we can get this into a decimal is to divide. So down number 5, and out goes on the outside of the square, sorry, square root, long division bar, and then the 3 would go in the inside. We know that 5 cannot go into 3 evenly, so we need to add a decimal and a 0, because 3.0 is the same as 3, and so we're adding zeros that will help us divide until we don't get any remainders. And now we're going to put our decimal up here. 5 could not go into 3, so we'll put a 0 to show that above the 3. And so now we'll take the next digit next to it, 0. So 5 goes into 30 6 times. And then remember, you're going to multiply this number times the 5 and write it underneath and see if there's any left. 6 times 5 is 30. And so there's nothing remaining for us to continue to divide. And so 3/5 as a decimal is 0.6. Let's do 5 6. So again, down and out, the 6 will go on the outside, and our 5 will go on the inside. Go ahead and put 1 0 after our 5 to see what we can do, because again, we'll put our decimal up here, and 6 could not go into 5. But how many times can 6 go into 50? Well, let's see here. 6 times 7 is 42. 6 times 8 is 48. 6 times 9 is 54. That's too much. So 8 times. And 8 times our 6 was 48. So when we subtract, we have a remainder of 2. And so that means we need to add a 0 after our first 0 that we added, so we can bring that down and keep dividing until we either get a 0 when we subtract for it to be finished, or we see a pattern, which will mean a repeating decimal. And so let's see, how many times can 6 go into 20? 6 times 3 is 18. 6 times 4 is 24. That's too much. So 3 times. And so 6 times 3 is that 18 that we just mentioned. And we subtract, and we get 2 left over. So notice we had a 2 here when we subtracted, and a 2 here when we subtracted. If we keep going on, we're going to get 3, which will have a difference of 2. And so that means that this 3 will keep repeating forever. We could keep dividing 10 pages worth, and we won't get anything different. And so 5 6 as a decimal is 0.83. Again, the bar above the 3 means that the 3 repeats. So now let's look at 8's 11ths and divide that out and see what we get. So again, down and out, our 11 goes on the outside, and our 8 goes on the inside. And we'll put a decimal. Let's put 2 zeros to start off with and see what happens. So 11 can't go into 8, so we'll put our 0 there in our decimal. 11 goes into 80. Well, 11 is easy to count by because we just keep changing the digits to the same thing. 11 times 7 would be 77. 11 times 8 would be 88, which is too much. So we have 7. And then 7 times 11 is 77. When we subtract, we get 3 left over. And so let's bring down our 0. And so 11 times 3 would be 33, which is too much. So we'll have to use 2. 11 times 2 is 22. When we subtract, we get 8. We still have a remainder. And so if we add a 0 and bring it down, notice we have 80. And here we had 80 when we divided. Here we're going to get 80 dividing. So we're going to get the same pattern that we get from the 80 down to the 80 again, which is the 7 and the 2 repeating. So both digits repeat. So the bar has to go above both of them. So 0.72 with a bar over both. So if you did that in the calculator, if you did 8 divided by 11, you would see across your screen 0.7272727, and it might say 3 because the calculator can only show so many, so it rounds that last space. But when you see that 72727272, you will always know that it's a repeating decimal. And so make sure that you show your work when you're doing these problems, but you can always check your answer in the calculator to see if you made a mistake. And then if you did, you can figure out where it was and correct it. Now let's look at inequality symbols. The symbols less than and greater than are called inequality symbols. So when it points to the left, that's less than. When it points to the right, that's greater than. And then notice the last two have lines underneath them. I always think of that as half an equal sign because when it points to the left and has a line, it's less than or equal to. And the pointing to the left with a line, greater than or equal to. So one way to think of it is it points to the smaller number and opens up to the bigger number because the point end is smaller than the opening end. And so we use these symbols to compare numbers together. And so for these examples, negative 14 compared to 20, I always think of negative as borrowing in this case, and I would rather have $20 than to borrow or owe somebody $14. And so we would put a less than sign. It points to the negative 14 because it's smaller, and it opens up to the 20 because it's larger. Now here, for B, we have negative 12 and negative 7. We know that 12 is bigger than 7, but this is negative. So again, if you think of money, is it better to owe somebody $7 or to owe them $12? Well, owing them $7 is better, so it's actually greater than. And so we have a less than symbol as well, because negative 12 is less than negative 7. And if you picture that on the number line, the negative 12 would be further to the left, and therefore it's a smaller number. And for the last one, we have 8 compared to negative 2. And a positive number is always bigger than a negative number. So we have a greater than symbol there. When we look at absolute value of a number, we're looking at the distance from 0 the number is on the number line. Because absolute value describes a distance, it is never negative. And so the absolute value of negative 3, should be another line there, is 3, because even if you're walking backwards, you're still traveling a distance. Distance is always positive. And 4, this absolute value is 4 as well, because, again, it's 4 spaces away from 0. So when we look at the examples here, for A, we have the absolute value of negative 2. So if we look up here, negative 2 is 2 spaces away from 0. So notice that our answer is always positive for that. And so when we look at the second one, though, notice we have a negative outside of it. So we want to make the answer of the absolute value negative. So the absolute value of negative 5 is 5, because negative 5 is 5 spaces away from 0. But then we have this negative on the outside, so we have to make the answer negative. The absolute value of 0 for C is 0 because it's right at 0, so it's no spaces away. And then for D, again, notice that we have a negative outside of the absolute value symbol. So the absolute value of 9.8 is 9.8, because it's 9.8 spaces away from 0. But then we have to take the negative of that answer, and so our answer is negative 9.8. So again, the only time you'll have a negative in your answer for absolute value is if there's a negative symbol outside of the absolute value symbol. So now let's compare problems with absolute value and our inequality signs. So let's simplify things first before we can compare them. This absolute value of negative 5 is positive 5 because it's 5 spaces away from 0. The absolute value of negative 9 is 9. So we see that 9 is greater than 5, so we'll put a less than symbol. For B, we have the absolute value of negative 5, which is 5. But again, we have the negative symbol on the outside, so that simplifies to negative 5. We have a negative 5 on the other side, so those are equal. For C, we have a fraction and a decimal compared. So let's get them both in the same form. I like to change my fractions into decimals because if I went to both fractions, I would need a common denominator to be able to compare them, and it's just a lot more work. So the absolute value of negative 3/4, again, 3/4 out of a dollar is 0.75, or again, we can divide 3 into 4 to get that. But then we have the absolute value on this side, having a negative on the outside, so we need to bring the negative down. And then the 0.8 stays the same. Now, sometimes it wants to confuse us a little bit by saying that our 75 has 2 spaces after the decimal, our 8 only has 1. But we can add, just like when we were dividing to get our decimals from our fractions, we can add what's called a terminal 0, a 0 at the end, and then we can compare them both with 2 digits. And so we can see that 75 compared to 80, 80 would be bigger, number 1, but we really don't have to go any farther than saying one's a negative and one's a positive. And so our positive is always bigger than our negative. So negative 0.75 is less than 0.8. And for our last one, we have the square root of 16. And we need to make that answer negative. The square root of 16 is 4. And we'll bring down the negative sign. So we're comparing negative 4 to negative 4. So that one is equal as well. Now let's look at rounding decimal numbers and whole numbers as well. Rounding means taking a number simpler, but keeping its value close to what it was. And so here we can see some place values nearest the decimal. To the left we have ones, then tens, hundreds, thousands. And to the right of the decimal, notice we don't have oneths. It starts with tenths, hundreds, thousands, 10,000s. So one way to distinguish if we're looking at before the decimal or after the decimal is the end of the word. Notice everything to the right of the decimal has THS at the end. So that's helping us distinguish between the tens spot, which is the 5 here, or the tenths spot, which is the 2. So when we're looking at rounding off whole numbers, we find the place value you want the rounding digit to be and look to the digit just to the right of it. If that digit is less than 5, we do not change the rounding digit, and we change all the digits to the right of the rounding digit to 0. If that digit is greater than or equal to 5, we add 1 to the rounding digit, or we make it the next number larger, and then change all the digits to the right of the rounding digit to 0. So let's look at some examples. For example 7, we're rounding to the nearest 10, And so notice there's no decimal places, but we know that it would understood to be afterwards. The 10 spot is second to the left from the decimal. So in this case, it's the 8. And the number that we need to help determine whether it stays in 8 or moves up to the 9 is the spot to the right of it, which is the 9. It is 5 or greater, so we bump the 8 up to a 9. And now that the 9 did its job, it turns into a 0. For 514, our 1 is a rounding digit. That's our 10th spot. The number to its right is a 4. A 4 tells it to stay the same. So we'll bring down our 5. A 1 stays the same. And everything else becomes 0, which is only 1 digit in this case, because we're rounding to the 10th spot. And our last number, 2,673. Again, our tens is located here at the 7. The number next to it that we look at is the 3. The 3 is below 5, so the 7 stays the same. So we'll bring down our 2 and our 6. The 7 stays the same, and our 3 becomes a 0. So rounding to the nearest 10, we get 2,670. Now let's look at rounding at the 100th spot. And so our 100th spot is third from the decimal. So again, if our decimal was written here, it would be the 8. Our 6 next to it tells us we need to bump it up to the next number, which is 9. And so the 6 did its job and it turns to 0, and anything after it turns into a 0. So we get 900. 549. Well, let's look at our 100 spot, which is the 5. The 4 next to it tells it to stay the same. So the 5 stays the same. The 4 turns to a 0, and anything after it turns to a 0. 3,979 to the nearest 100. So we're looking at our 9 in our 100 spot. The 7 tells us to round up. But notice our 9 rounded up to the next number would be 10. So we'll put our 0 for our 10, but then we have to, just like adding, carry the 1. And so that 1 from the 10 adds to the 3 to become 4. And then the 7 turns into 0, and anything after it turns into a 0. So we actually get 4,000 when we round to the nearest 100 for that problem. Now let's take a look at rounding to the nearest 1,000. 1,000 is easy to find because it's the number just to the left of our first comma. And so our 4 is in our thousands spot. The 3 is next to it, which tells us to stay the same. So the 4 stays the same, and all the digits after turn into zeros. For 56,567, our 6 is in our thousands spot. Oops. Keep it consistent. We'll circle the 6. And our 5 to the right of it tells us to bump up. So we'll bring down the 5, change our 6 to a 7, and then every digit after it turns to zeros. So 57,000. And 89,743. So our thousand spot is the 9. The number to the right of it is the 7. It tells us to bump the 9 up to a 10. So again, we'll have to add that 1 from the 10 to the 8 in front of it to make it a 9. And then everything after turns into zeros. So 89,743 rounded to the nearest 1,000 is 90,000. Now let's look at decimals. Find the place value you want to round to, the rounding digit, just like we did before, and look at the digit to the right of it. If that digit is less than 5, do not change the rounding digit, but drop all the digits to the right of it. If that digit is greater than or equal to 5, add 1 to the rounding digit and drop all the digits to the right of it. So the reason that they changed the explanation, because when we have zeros to the right of the decimal, we have them, I mentioned earlier, they're called terminating decimals. So for example, if we have 0.1 or 0.10 or 0.100, it's all the same value. And so we can look at this as 1/10, 10 hundredths, or 100 thousandths, but it's all the same because a zero after the digits at the end are not important, so they get dropped. And that's why it says just to drop all the digits, because they're not necessary. They turn into zeros, and zeros at the end are called terminating zeros. They are not needed. They're helpful when we're looking at comparing decimals, but they don't change the value and they're not needed. And so we simplify the number by just dropping those zeros. So our examples first are to round to the nearest tenth. So here's our 10th spot. So we're going to drop everything but one space after the decimal, because again, that's the 10th spot. So anything in front of the decimal will just bring down. And then the 8 tells our 5 to round up to a 6. And the 8 has done its job. So again, it becomes a 0, which we don't need to write. It just disappears. 2 and 349 thousandths is how you would read that. But we're looking at our 3 in our 10th spot and using the 4 to change it or keep it. The 2 in our decimal place drops down. The 4 says to leave the 3 alone. And then the 4 and everything behind it turns into zeros, which again, we don't have to write because they don't change the value of anything. And 8.1736, our 10th spot is a 1. And we're using the 7 to tell us to move it up to a 2. So 8.2000. Again, those zeros we don't write. And so we have just 8.2. So notice all our answers only has the 10th spots. Next, we have rounding to nearest hundredth. So we'll have 2 spaces in our answer because 10th spot, 100th spot. We're rounding to the 100th, so we're going to look at the 9. And the 4 tells us to keep the 9 the same, so everything in front of it, we drop down. The 9 stays the same, and the 4 we're done with. Next number, 9.973. So our 100th spot is the 7. The 3 tells us to leave it alone. And so we have 9.97. And then we have 1.1536. So again, the hundredths is 2 spaces to the right of the decimal. The 3 tells us to leave the 5 alone. So we'll have 1.15. And then the 3 and the 6 are gone. So now let's round the last 3 numbers here to the nearest dollar. Ooh. If we think of money, our dollar is in our ones spot. So we're going to look at the number to the left of the decimal. And so we need the number to the right of the decimal to help us with that. And so the 5 tells us to round up. So 9 becomes 10. So there's a 0, put a 1 up here, and then add those together to get 5. So $49.57 would round to $50. 141.17. So again, the 1 is in our dollar spot, and there's also 1 in our 10th spot that tells us to keep the 1 alone. So 1 for keep this 1 and drop the cents, so $141. And then $8,173.62. The 3 is in our 1. The 6 tells us to round up. So we'll bring down the 8, 1, the 7, and change the 3 to a 4. So we have $8,174 when we round. And now it's time for you to practice. So on pages 11 and 12 in your workbook, there's practice problems for you to try. If you have any difficulties with them, please shoot me an email. Otherwise, I'll see you next time.